Hey everyone! So we are going to start our new material with the periodic table, which is where we left off before we left school. And I figured since it's been a little while, we are going to start with an article about the periodic table and how it sort of began, which I know we already talked about, but like I said, it's been a little while. So I know I could just give you the article, but that to me feels a little bit boring, and it's not how we did things in class. So I am going to post the article on Google Classroom once I'm done, but I'm going to read it here like we did in class, and I'm going to ask you guys to watch the video. That way you can read along with me just like we did in class, and then I'll post some questions that I want you to answer. This way you can read along with me, and I can kind of emphasize what's important in the article, and then you can answer the questions once I'm finished. I am looking down at a computer screen which is in front of me. I'm pretty sure you can't see that in the video, sorry, but it's why I might not be looking at the camera the whole time. Alright, I just want to say I do miss you guys. I miss being in class with you, but this is sort of the best we can do at the moment. So, the title of our article, which you can probably see now since you should have it in front of you, is How the Periodic Table Went from a Sketch to an Enduring Masterpiece. So, we start. Every field of science has its favorite anniversary. For physics, it's Newton's Principia of 1687, the book that introduced the laws of motion and gravity. Hopefully we remember that from class. Biology celebrates Darwin's On the Origin of Species, 1859, along with his birthday, 1809. Hopefully you remember that from bio with Mr. Farnham. Astronomy fans commemorate 1543, when Copernicus placed the sun at the center of the solar system. Ooh, we learned about that. And for chemistry, no cause for celebration surpasses the origin of the periodic table of the elements, celebrated 150 years ago this March by the Russian chemist Dmitry Ivanovich Mendeleev. We learned about that a little bit ago. Mendeleev's table has become as familiar to chemistry students as spreadsheets are to accountants. It summarizes an entire science in 100 or so squares containing symbols and numbers. It enumerates the elements that compose all earthly substances, arranged so as to reveal patterns in their properties, guiding the pursuit of chemical research both in theory and in practice. So I'm going to pause. Hopefully we remember from class, and as we go through the next couple weeks, we will talk about on here the periodic trends, such as atomic size, such as electronegativity, ionization energy. Hopefully remember, sort of jogging our memory as I'm saying it. We'll go through that again, sort of in brief, because again, we already talked about it, but hopefully this is jogging our memory a little bit. All right, jumping back in. The periodic table, wrote the chemist Peter Atkins, is arguably the most important concept in chemistry. Mendeleev's table looked like an ad hoc chart, but he intended the table to express a deep scientific truth he had uncovered, the periodic law. His law revealed profound familial relationships among the known chemical elements. They exhibited similar properties at regular intervals or periods when arranged in order of their atomic weights, and enabled Mendeleev to predict the existence of elements that had not yet been discovered. Before the promulgation of this law, promulgation means start or beginning. Before the promulgation of this law, the chemical elements were mere fragmentary, incidental facts in nature. Mendeleev declared, the law of periodicity first enabled us to perceive undiscovered elements at a distance which formerly was inaccessible to chemical vision. So what he's saying here is that before the start or the discovery of this law, the chemical elements were just sort of like part of nature, but they weren't like brought together. They were just sort of like all over the place and nobody brought them together. He was bringing them together to show how they relate to each other. So coming back in, Mendeleev's table did more than foretell the existence of new elements. It validated the then controversial belief in the reality of atoms. It hinted at the existence of subatomic structure and anticipated the mathematical apparatus underlying the rules governing matter that eventually revealed itself in quantum theory. His table finished the transformation of chemical science from the medieval magical mysticism of alchemy to the realm of modern scientific rigor. The periodic table symbolizes not merely the constituents of matter, but the logical cogency and principled rationality of all science. So again, what we're saying here is that back, again, ancient Greece, when we first saw, remember when we were talking about the history of atomic structure, when we first saw atoms might exist, we didn't have any proof. So Mendelev's table says, yeah, atoms exist. But it did a little bit more than that. It also said, not only do they exist, might be subatomic particles, protons, neutrons, electrons. And it also, as it says here, is that mathematical apparatus they reference. Sorry. It's also giving rise to, and this is a little bit beyond the scope of our course, really beyond the scope of any high school course, but it also allows quantum theory to start essentially becoming an actual physical science, as opposed to, as they say, sort of a mystical belief. Okay, so we're going to skip over the diagram. Laying the groundwork. Legend has it that Mendeleev conceived and created his table in a single day, February 17th, 1869. On the Russian calendar, March 1st in most of the rest of the world. But that's probably an exaggeration. I would think so. Mendeleev had been thinking about regrouping the elements for years, and other chemists had considered the notion of relationships among the elements several times in the preceding decades. In fact, German chemist Johann Wolfgang Dobrinner noticed peculiarities in groupings of elements as early as 1817. In those days, chemists hadn't yet fully grasped the nature of atoms as described in the atomic theory proposed by English schoolteacher John Dalton in 1808. There's a name we know. In his new system of chemical philosophy, Dalton explained chemical reactions by assuming that each elementary substance was made of a particular type of atom. Chemical reactions, Dalton proposed, produced new substances when atoms were disconnected or joined. Any given element consisted entirely of one type of atom, he reasoned, distinguished from other kinds by weight. Oxygen atoms weighed 8 times as much as hydrogen atoms. Carbon atoms were 6 times as heavy as hydrogen, Dalton believed. When elements combined to make new substances, the amounts that reacted could be calculated with knowledge of these atomic weights. Dalton was wrong about some of the weights. Oxygen is really 16 times the weight of hydrogen, and carbon is 12 times heavier than hydrogen. But his theory made the idea of atoms useful, inspiring a revolution in chemistry. Measuring atomic weights accurately became a prime preoccupation for chemists in the decades that followed. When contemplating those weights, Dobrinner noted that certain sets of 3 elements, he called them triads, showed a peculiar relationship. Bromine, for example, had an atomic weight midway between the weights of chlorine and iodine. In all 3 elements, all 3 elements exhibited similar chemical behavior. Lithium, sodium, and potassium were also a triad. Other chemists perceived links between atomic weights and chemical properties, but it was not until the 1860s that atomic weights had been well enough understood and measured for deeper insights to emerge. In England, the chemist John Newlands noticed that arranging the known elements in order of increasing atomic weight produced a recurrence of chemical properties every 8th element, a pattern he called the law of octaves, in an 1865 paper. But Newland's pattern did not hold up very well after the first couple octaves, leading a critic to suggest that he should try arranging the elements in alphabetical order instead. Clearly, the relationship of element properties and atomic weights is a bit more complicated, as Mendeleev soon realized. So it kind of sounds like we've got a couple of people here, right? We've got Dalton, who we already know about, right? He was in our atomic structure book. And then we've got Newlands. We've also got Dobrinner. And they all kind of have these different ideas. So we have Dalton, who has this idea that we should figure out the weight of the atoms. He didn't really have an arrangement for them. He was just figuring out weights. Then we have Dobryner, who's putting them into triads based on how they weigh. And then we have this guy Newlands, who's putting them into octaves, groups of 8, based on how they weigh. It seems like Dobryner and putting them into the triads kind of worked. Seems like Newlands and his octaves kind of didn't. And then this critic guy with his alphabetical order, we definitely know that doesn't work because the periodic table is not alphabetical. So we've got some conflicting ideas. So what we're going to do now, we're going to go through the next section, organizing the elements, and then we're going to stop. I know that's not the end of the article, but we're going to go through the next section, and then we're going to stop for today, and we'll do the rest of the article tomorrow. So, organizing the elements. Born in Tobolsk, Siberia in 1834, his parents' 17th child, Mendeleev lived a dispersed life, pursuing multiple interests and traveling a higgledy-piggledy path to prominence. So he apparently studied a whole bunch of stuff and sort of went all over the place to figure out what he wanted to do. During his higher education at a teaching institute in St. Petersburg, he nearly died from a serious illness. After graduation, he taught at middle schools, a requirement of his scholarship at the teaching institute, and while teaching math and science, he conducted research for his master's degree. He then worked as a tutor and lecturer, along with some popular science writing on the side, until earning a fellowship for an extended tour of research at Europe's most prominent university chemistry laboratories. When he returned to St. Petersburg, he had no job, so he wrote a masterful handbook on organic chemistry in hopes of winning a large cash prize. It was a long shot that paid off, with the lucrative Demidov Prize in 1862. He also found work as an editor, translator, and consultant to various chemical industries. Eventually, he returned to research, earning his PhD in 1865, and then becoming a professor at the University of St. Petersburg. Soon thereafter, Mendeleev found himself about to teach inorganic chemistry. In preparing to master that new, to him, field, he was unimpressed by the available textbooks. So he decided to write his own. Organizing the text required organizing the elements, so the question of how best to arrange them was on his mind. So this guy's done a lot, obviously, and it's incredible to me how many different fields he was in and how many different things he did, and honestly, he wasn't all that old, right? So at this point, it's 1865, and he was born in 1834, so he's only 31 at this point. All right, so by early 1869, Mendeleev had made enough progress to realize that some groups of similar elements showed a regular increase in atomic weights. Other elements were roughly equal atomic weights, shared common properties. It appeared that ordering the elements by their atomic weight was the key to categorizing them. By Mendeleev's own account, he structured his thinking by writing each of the 63 known elements' properties on an individual note card. Then, by way of a sort of game of chemical solitaire, he found the pattern he was seeking, arranging the cards in vertical columns from lower to higher atomic weights, placed elements with similar properties in each horizontal row. Mendeleev's periodic table was born. He sketched out his table on March 1st, sent it to the printer, and incorporated it in his soon-to-be-published textbook. He quickly prepared a paper to be presented to the Russian Chemical Society. Elements arranged according to the size of their atomic weights show clear periodic properties, Mendeleev declared in his paper. All the comparisons which I have made lead me to conclude that the size of the atomic weight determines the nature of the elements. Meanwhile, the German chemist Lothar Meyer had also been working on organizing the elements. He prepared a table similar to Mendeleev's, perhaps even before Mendeleev did, but Mendeleev published first. And in science, that's what's important, unfortunately. Meyer's actually not really a name that most people know, but most people are pretty sure that Meyer developed his table first. All right. More important than beating Meyer to the publication punch, though, was Mendelev's use of his table to make bold predictions about undiscovered elements. In preparing his table, Mendeleev had noticed that some note cards were missing. He had to leave blank spaces to get the known elements to properly align. Within his lifetime, 3 of those blanks were filled with previously unknown elements: gallium, scandium, and germanium. Not only had Mendeleev predicted the existence of these elements, but he had also correctly described their properties in detail. Gallium, for instance, discovered in 1865, had an atomic weight, as measured then, of 69.9 and a density of 6 times that of water. Mendeleev had predicted an element, he called it eka-aluminum, with just that density and an atomic weight of 68. His predictions for eka-silicon closely matched germanium, discovered in 1886, in atomic weight 72 predicted and 72.3 observed, and density 5.5 versus 5.469. So he was actually able to use the periodic table that he created to predict where elements that hadn't been discovered yet should go, which made his periodic table better than what Meyer had put together, because Meyer was not able to use what he put together to predict unknown elements. He also correctly predicted the density of germanium's compounds with oxygen and chlorine. Mendeleev's table had become an oracle. It was as if end-of-game Scrabble tiles spelled out the secrets of the universe. While others had glimpsed the periodic law's power, Mendeleev was the master at exploiting it. Mendeleev's successful predictions earned him legendary status as a maestro of chemical wizardry. But today, historians dispute whether the discovery of the predicted elements cemented the acceptance of his periodic law. The law's approval may have been more due to its power to explain established chemical relationships. In any case, Mendeleev's prognosticative accuracy certainly attracted attention to the merits of his table. By the 1890s, chemists widely recognized his law as a landmark in chemical knowledge. In 1900, the future Nobel Chemistry laureate William Ramsay called it the greatest generalization which has as yet been made in chemistry. And Mendeleev had done it without understanding in any deep way why it worked at all. Okay, so I know there's a few pages left here. We're actually going to stop. Actually, I lied. There's about a page and a half. All right, we'll finish this up. I thought there were 3 pages left. All right, we'll finish this up for the moment, and then I'm going to post questions in a little bit, and we will move on with information about the periodic table tomorrow. All right, so let's finish up the mathematical map. No, we're just going to stop there. I'm sorry. All right, so we're going to stop there. I know, like I said, I know there's one more section, but yeah. All right, so we're going to stop there. I am going to post this video, and I'll post questions with it. I do want you to go through the questions and submit them on Google Classroom to me, okay? And I'll post instructions on Google Classroom for how you're going to do that, all right? So I don't want to say see you guys in a little bit, because unfortunately I don't get to see you, but I'll talk to you guys in a little bit, okay?